ERO. 53.9 kilometers of tunnel, bored through fractured volcanic rock beneath a strait where tectonic plates collide. That single number made the Seikan Tunnel the longest rail tunnel on Earth for more than 2 decades. But length was never the real problem. The real problem was water, moving through cracks in a seabed shaped by earthquakes, flooding the bore faster than any pump could handle. The Tsugaru Strait separates Japan's 2 largest islands, Honshu, the densely populated mainland, and Hokkaido, the second largest island and the northernmost of Japan's 4 main landmasses. For most of modern history, the only connection between them was a fleet of ferries crossing some of the most violent waters in the North Pacific. Typhoons swept through the strait with little warning. Winter storms battered ships with devastating regularity. The need for a fixed crossing was not abstract. It was measured in lives lost at sea and in the economic isolation that kept an entire island peripheral to the national economy. So engineers proposed what seemed like a straightforward solution: bore a railway tunnel under the strait, link the 2 islands permanently, and eliminate dependence on weather-vulnerable ferries. The promise was elegant. Connect Honshu and Hokkaido by rail, bring northern Japan into the economic mainstream, and end the deadly gamble of open water crossings. The geology beneath the strait, however, had other plans. What made this strait uniquely hostile to tunneling was not merely its width, but its subsurface character. The seabed beneath the Tsugaru Strait is not stable continental shelf. It sits in one of the most seismically active corridors on the planet, where the Pacific Plate drives beneath the North American Plate. The rock is a fractured patchwork of volcanic deposits, mudstone, and fault zones saturated with pressurized seawater. No amount of survey data could fully map the extent of those fractures before excavation began. Engineers understood from the earliest surveys that any tunnel through this ground would be fighting water at every meter of advance. The fractures were not isolated cracks. They formed interconnected networks that could channel seawater deep into excavation zones under enormous hydrostatic pressure. This was not a problem that could be solved simply by making walls thicker or pumps bigger. Initial investigations began with pilot bores, narrow exploratory shafts driven ahead of the main tunnel alignment to map geological conditions in real time. These advanced tunnels revealed the true scale of the challenge. At multiple points, pressurized groundwater broke through fractured rock with force sufficient to fill working chambers in minutes. The water came cold and relentless, carrying the full weight of the ocean above. Early flooding events halted construction entirely, forcing evacuations and months of remedial work. Workers faced conditions where the rock itself seemed to resist penetration, releasing torrents of cold seawater through networks of interconnected fissures that no survey had fully predicted. Each flood was not just a delay. It was a signal that the conventional approach of excavate first, then waterproof, could not work in this geology. The ground had to be controlled before it was cut. The turning point was not a single invention, but an engineering philosophy. Accept that you cannot seal fractured volcanic seabed permanently with concrete alone. Instead, the project developed a systematic approach to chemical injection grouting performed ahead of excavation. This was the decision that made everything else possible. Before cutting a single meter of new tunnel face, crews drilled probe holes forward into unexcavated rock. If water appeared, and it almost always did, they injected chemical grout under pressure into the surrounding fracture network, binding loose material and blocking water pathways before the main bore reached that zone. The tunnel was being stabilized before it was being dug. The ground ahead was treated as hostile territory to be neutralized in advance. This preemptive grouting system transformed the construction logic entirely. Rather than reacting to flooding after the fact, engineers treated the ground ahead as a problem to be solved before it became a crisis. The technique required extraordinary patience. Each advanced cycle involved drilling, testing, injecting, waiting for the grout to cure, then testing again before excavation resumed. If the tests showed continued water infiltration, the cycle repeated. Progress sometimes slowed to a few meters per day, but the method gave crews a reliable way to stabilize rock that would otherwise have been uncontrollable. Speed was sacrificed deliberately for certainty. In a seismic zone beneath the ocean floor, where a single catastrophic inflow could drown an entire working face, certainty was worth more than pace. The approach came at extraordinary cost in both time and resources. The total construction period stretched across more than 2 decades, making it one of the longest infrastructure projects in modern Japanese history. The undersea portion alone required engineering teams to maintain continuous pumping operations even after sections were nominally complete, because the fractured geology continued to admit small volumes of water that accumulated steadily over time. The tunnel was not simply built and sealed. It requires ongoing drainage management as a permanent operating condition. This was not a flaw in the design. It was the design itself, built into the operational budget and maintenance schedule from the beginning. Not every expert agreed this was the optimal solution. Some engineers argued that an immersed-tube approach, sinking prefabricated sections into a trench cut in the seabed, might have been faster and cheaper in such difficult geology. Others pointed out that seismic risk made a rigid immersed structure more vulnerable to displacement during major earthquakes, whereas a bored tunnel deep in rock could flex with the surrounding ground during seismic events. This debate was never fully resolved by the project's completion. The choice of a deep-bored alignment reflected Japan's assessment that seismic resilience mattered more than construction speed or cost efficiency. In a country where magnitude 7 earthquakes are not rare events, but recurring certainties, that judgment carried weight that pure cost analysis could not capture. The decision to route the tunnel roughly 100 meters below the seabed, rather than closer to the surface, was itself a direct response to earthquake risk. At that depth, the surrounding rock provides confinement pressure that helps resist the shaking forces transmitted during seismic events. A shallower alignment would have encountered weaker surface sediments and greater vulnerability to seafloor displacement along fault traces. Depth brought punishing water pressure challenges, but purchased the structural stability needed for a century of operation. Today, the Seikan Tunnel carries rail traffic between Honshu and Hokkaido, including high-speed Shinkansen services that reduce travel time between the islands from hours by ferry to minutes by train. The tunnel that was once the longest rail tunnel in the world held that distinction until the Gotthard Base Tunnel opened in Switzerland. But the Seikan Tunnel remains the longest tunnel with an undersea section, and it continues to operate in a seismic environment that has not grown quieter since its construction. Continuous monitoring systems track ground movement, water inflow rates, and structural deformation along the full length of the bore. Pumping stations run without interruption, day and night, year after year. The tunnel is not a static structure sealed against nature. It is an active system, maintained against the same geological forces that nearly defeated its construction decades ago. What the Seikan Tunnel demonstrates is not that human engineering can overpower geology. It demonstrates the opposite. The breakthrough was accepting that fractured, seismically active rock cannot be conquered in a single construction campaign. It must be managed continuously. The chemical grouting technique that made excavation possible was not a permanent seal. It was a method of buying enough stability to advance. The pumping systems that keep the tunnel dry today are not a failure of waterproofing. They are the designed operating condition of a structure that exists inside a living geological system. Every day that trains cross the Tsugaru Strait underground, they pass through rock that is still shifting, still emitting water, still responding to the tectonic forces that fractured it millions of years before anyone considered putting a tunnel there. The engineering decision that made the Seikan Tunnel possible was not finding a way to stop the water. It was designing a system that could live with it indefinitely. The strait is no quieter now than it was when construction began. The tunnel endures not because it defeated the geology, but because it was built to coexist with forces that will outlast any human structure. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.